Let's move on to section 3.6, the last part of Thermochem lecture. Standard enthalpy change of solution. It is the heat change when 1 mole of a substance is completely dissolved in enough water under standard conditions of 298 Kelvin and 1 bar so that there is no further heat change upon adding more water. In our syllabus, the substance refers to the ionic compound. It can be determined experimentally using this formula, and the units kilojoules per mole. Per mole here refers to per mole of substance dissolved. And this process can be negative or positive because not all ionic compound can dissolve in water. To represent this process using a thermochemical equation, it will be for 1 mole of ionic compound to be completely dissolved in water to give aqueous ions. For example, sodium chloride. To represent enthalpy change of solution for sodium chloride, the equation will show 1 mole of sodium chloride solid dissolved in water to give aqueous sodium plus and Cl minus ions. Likewise for copper sulfate. To represent enthalpy change of solutions for copper sulfate, the equation has to be 1 mole of copper sulfate solid dissolved in water to give aqueous copper 2 plus ions and sulfate ions. Remember, the substance has to be in 1 mole. And the enthalpy process can be positive or negative. A more negative enthalpy change of solution will tell you that this ionic compound is more soluble in water. Note that even though sodium chloride has a positive enthalpy change of solution, it doesn't mean that sodium chloride is insoluble in water, because we have observed sodium chloride, which is the table salt, is soluble in water. It just means that it is less soluble in water compared to copper sulfate. In fact, the room temperature of the water can supply enough energy to dissolve sodium chloride in water, because the enthalpy change of solution is a very small positive number. It is only slightly endothermic. So the last process you need to know is the standard enthalpy change of hydration. It is the heat evolved when 1 mole of gaseous ions is hydrated under standard conditions of 298 Kelvin and 1 bar. And this process is always exothermic because it involves bond formation process. It involves formations of ion dipole interaction between the ions and the water molecule to give aqueous ions. So this is the ion dipole interaction between the ions and the polar water molecule. And the energy released is dehydration energy. To represent this process using a thermochemical equation, it will be showing 1 mole of gaseous ions to form 1 mole of aqueous ions. So therefore, from the above relationship, the larger the ionic charge, the greater will be the charge density of the ion, the larger will be the magnitude of enthalpy change of hydration. Or the larger the ionic radii, the smaller the charge density of ions, the smaller will be the magnitude of enthalpy change of hydration. So from this table, you can see that as the ionic charge get bigger, the enthalpy change of hydration become more exothermic, or the magnitude of enthalpy change of hydration become bigger. Likewise, as the size of ions get bigger, you find that the enthalpy change of hydration become less exothermic, or the magnitude of enthalpy change of hydration becomes smaller. Let's do exercise 27 together. Explain why the enthalpy change of hydrations of halides ion become less exothermic going down group 17. This is the table of data. This is the halides ion. As you go down group 17, you find that the enthalpy change of hydration become less exothermic. So why? Recall, the magnitude of enthalpy change of hydration of ion is dependent on the charge density of the ion, which is directly proportional to the charge of ion and inversely proportional to the ionic radius of the ion. So therefore, going down the group, the ionic charge of halide ion is the same. everyone has a charge of -1, while the ionic radius of the ion increases down the group, because as you go down the group, it increase number of principal quantum shell, so the radius will increase. Thus, the charge density of halide ion decreases down group 17. When the charge density of ion becomes smaller, then the strength of ion-dipole interaction between halide ion and water molecule will become weaker. So therefore, going down group 17, the strength of ion-dipole interaction between halide ion and water molecule decreases. Hence, the magnitude of enthalpy change of hydration of halide decreases, or the enthalpy change of hydration of halide ion become less exothermic as you go down group 17. Let's look at the relationship between enthalpy change of solution, enthalpy change of hydration, and lattice energy. To dissolve an ionic compound involves two processes. The first process is to break down the ionic lattice, is to break the ionic bonds to form its constituent gaseous ions. And this process is the reverse of lattice energy, as energy is absorbed to break the ionic bond. And once the gaseous ion is formed, each ions will be hydrated through formations of ion-dipole interaction with water molecule. And this process releases energy. This process is the enthalpy change of hydration. Let's take a look at figure 8, which shows a simplified illustration of processes during the dissolution of an ionic compound. For an ionic compound, example, solid sodium chloride, to undergo enthalpy change of solution to form its aqueous cation and aqueous anion, the ionic lattice must first be broken down by absorbing sufficient energy to break all the ionic bonds in the lattice to form its gaseous cation and anion. This amount of energy is the lattice energy, as breaking of ionic bond is the reverse of the lattice energy process. So you reverse the lattice energy to form gaseous cation and anion. Once the gaseous ions are formed, each of the ions will be hydrated to form aqueous ion. So this is the sum of the enthalpy change of hydration processes. So by Hess's law, the enthalpy change of solution, which is the direct path, will be equal to, this is the indirect path, minus the lattice energy plus sum of the enthalpy of hydration processes. So this is the equation to find enthalpy of solution of ionic compound. Looking closely at this equation, minus lattice energy refers to energy absorbed to break the ionic bond. This is the positive term. Sum of the enthalpy of hydration of ion is the energy released from the ion-dipole interactions. This is the negative term. Let's use calcium chloride as an example to illustrate how we can construct an energy cycle to link up enthalpy change of solution, lattice energy, and enthalpy change of hydration process. I'll start with the enthalpy change of solution of calcium chloride to give its aqueous ions. Equation must be balanced, so it gives 2 moles of Cl minus and 1 mole of Ca2 plus aqueous ion. 1 mole of CaCl2 ionic compound can form from its lattice energy from its gaseous ion. So from 1 mole of Ca2 plus gaseous ion and 2 moles of Cl minus gaseous ion. This is the lattice energy of CaCl2. And the gaseous ions can undergo hydration. So this is the enthalpy change of hydration of Ca2 plus. The 2 moles of chloride can also undergo hydration. So this is enthalpy change of hydration of Cl minus. Since 2 moles of chloride undergo hydration, so times 2. So by Hess's law, the enthalpy change of solution of calcium chloride, this is the direct path. This will be the indirect path. It will be equal to minus lattice energy of calcium chloride plus enthalpy change of hydration of Ca2 plus 2 times enthalpy change of hydration of Cl minus. So this is the equation to calculate enthalpy change of solution of ionic compound. And remember, minus lattice energy is a positive term. It's the energy needed to break the ionic bonds. And sum of the enthalpy change of hydration of ion is the negative term. It is the total energy released from the ion dipole interaction. So from the relationship, if the enthalpy change of solution is a very positive number, it's highly endothermic, which means the magnitude of lattice energy is much greater than the magnitude of enthalpy change of hydration of ions. This means that the energy released from the formation of ion dipole interaction is insufficient to compensate the energy needed to break the strong ionic bonds. So this substance will be generally less soluble in water or sparingly soluble in water. If the enthalpy change of solution is negative, which means the negative term is bigger than the positive term, the magnitude of enthalpy change of hydration is greater than the magnitude of lattice energy. This means that the energy released from the ion dipole interaction is more than sufficient to compensate the energy required to break the ionic bond. So this substance is generally more soluble in water. Let's do exercise 28 together. You are given 3 enthalpy processes. Enthalpy change of solution of potassium bromide. This is the equation. Enthalpy change of hydration of potassium ion. Enthalpy change of hydration of bromide ion. You are to construct an energy level diagram and use it to calculate lattice energy of potassium bromide. The equation to represent lattice energy is to form 1 mole potassium bromide from the gaseous ions. So it's on K plus and Br minus gaseous ion. So this is the equation for lattice energy of potassium bromide. From the equations of the given enthalpy processes and lattice energy, I will start with the species that has the highest energy, the most unstable state, which will be the gaseous ions. So I start from the gaseous ion at the top of the energy level diagram. So I start from K plus and Br minus gaseous ion. Next, let's incorporate the given data into the energy level diagram. From the gaseous ion, let's do enthalpy change of hydration to convert them to aqueous ions. So let's do enthalpy change of hydration of potassium ion first to convert K plus gas ion to K plus aqueous ion. This enthalpy process is minus 322, arrow is pointing down. Since nothing has been changed to Br gaseous ion, I'll put it down to balance the equation. Next, I'll do the hydration of Br minus ion to convert Br minus to Br aqueous ion. The enthalpy process is minus 336, so arrow is pointing down. To balance the equation, I'll put back K plus aqueous. Next data is the enthalpy change of solution. It's given to you as plus 20. Plus 20 means arrow is pointing up to the aqueous ions. So the energy level of potassium bromide will be lower than its aqueous ion. So the arrow is pointing up. This is 20. So from the gaseous ion to the ionic compound, this is the lattice energy of potassium bromide. To find the enthalpy change for this process, you can go by Here's law. So by Here's law, this is the direct path to bring the initial state to the final state. You can go by the indirect path, which is this path. So by Here's law, the enthalpy change of lattice energy of bromide, potassium bromide, will be equal to minus 322 plus minus 336 minus plus 20. So you have minus 678 kilojoules per mole. If the question did not ask for an energy level diagram, then you can use a simple energy cycle to solve. I'll start with the enthalpy change of solution for potassium bromide. So KBr solid to give aqueous ion. This is enthalpy change of solution of potassium bromide. The given enthalpy process is plus 20. So this is plus 20. Then I'll link up lattice energy. This is the lattice energy of potassium bromide from the gaseous ion. And this process is what you want to find. Then the gaseous ion will undergo hydration. So hydration of K plus ion, this is given to you as minus 322. And the bromide ions will undergo hydration. So this process is given to you as minus 336. So you can apply Hess law to this simple energy cycle, you get the same answer. Last part of lecture notes provide a summary for definitions and formulae. To do well in this energetics, you must memorize all the definition and be able to convert each definition to a thermochemical equation to represent the process. So please memorize the whole definition using this summary, and then you will complete this extension summary exercise. The tutor will go through the answers with you in the tutorial.